Today, we're pulling off a heist, a chemical heist. We're going to crack the code on the great metal escape, how we spring the metals we use every single day from the rocks they're locked inside.
No, really, just for a second, look around you. The phone you might be holding, the fork you ate with, the bike you ride, it's all metal. But here's the thing, none of it started out shiny and pure. It all had a much rockier beginning.
Yep, the answer is literally right under our feet, in the ground. You see, most metals are trapped, chemically handcuffed to other elements inside what look like pretty ordinary rocks. So the big question is, how do we bust them out?
All right, let's get into it. To figure out the escape plan, first we gotta understand the prison itself.
And that prison is called a mineral. You can think of a mineral as a kind of natural chemical recipe. It's a very specific mix of different elements all bonded together. And the key ingredient we're after, of course, is the metal hidden inside.
And here's the crucial part. Metals are rarely just sitting there waiting for us. They're usually in a chemical partnership. Iron, for example, loves to bond with oxygen, forming iron oxide, which we find in a mineral called hematite. Same with copper. It's often locked inside that beautiful green mineral malachite.
And when I say partnership, sometimes it's more like a giant chaotic party. Just look at this thing, eudialyte. Its chemical formula has over 100 atoms from 9 different elements all tangled up. Now, just imagine trying to pick out only the iron atoms from that mess. It's wild.
So how in the world do we know which tool to use for which job? Well, it all comes down to one simple but super powerful concept. I like to call it the reactivity rulebook. So what is reactivity? You can think of it as a metal's chemical personality. How badly does it want to react with other things? A really reactive metal has a super strong grip on whatever it's bonded to, which, you guessed it, makes it way harder to separate. And this right here is the master key, the reactivity series. It's basically a power ranking. At the very top, you've got the most reactive metals, like potassium, and way down at the bottom, the least reactive, like gold. But look closely. See that one non-metal in the middle? Carbon? Its position on this list is the secret to pretty much everything we're about to talk about.
Okay, so let's start at the bottom of that power ranking with the easiest cases of all. This is what I call the easy grab.
Gold and silver, they're kind of the loners of the chemical world. They're so unreactive, so uninterested in bonding with other elements, that you can literally find them as pure little nuggets and flakes just sitting inside rocks. No crazy chemistry needed, just find them, crush the rock, and melt the metal out. Easy.
All right, things are about to get a little more interesting. Moving up the ladder, for the next group of metals, we have to be a bit more clever. Welcome to the carbon swap.
So metals like zinc, iron, and copper are a bit more social. They're almost always bonded with oxygen, in compounds we call metal oxides. To get the pure metal, we can't just crush the rock anymore. We have to break that chemical bond. And this is where our old friend carbon comes into play. Remember the reactivity series? Carbon is more reactive than these metals. So if you take that metal oxide and heat it up with carbon, the carbon basically swoops in and steals the oxygen away. It's a fantastic chemical trade that leaves the pure metal behind.
The fancy term for this is a displacement reaction. The more reactive element kicks the less reactive one out of its partnership. It's like a stronger dancer cutting in on the dance floor. And because we're taking oxygen away, the specific process gets its own name, reduction with carbon.
But what happens when carbon isn't the stronger dancer? Well, for the metals at the tippy top of our reactivity series, we have to stop being clever and just bring out the heavy machinery.
Let's take a look at aluminium. It's way above carbon on that power ranking. What that means is that aluminium has a much stronger grip on oxygen than carbon could ever hope to have. So our carbon swap trick is completely useless here. Carbon just isn't strong enough. To break this incredibly powerful bond, we have to resort to brute force, a massive jolt of electricity. This process is called electrolysis, and it takes a truly staggering amount of power, which explains why making brand new aluminum is so energy intensive.
And this really sums it all up, doesn't it? If a metal is less reactive than carbon, we use that clever chemical swap. But if a metal is more reactive than carbon, we have no choice but to use the power play, electrolysis, using raw electricity to just rip the compound apart.
So now that you know the rules of the game, you can actually start to think like a chemist. You can start making predictions.
All right, let's try one. Let's say we have lead. We know it sits somewhere between iron and copper on the reactivity series. So based on everything we've just talked about, what's your guess? How do we get lead out of its ore?
Let's walk through it together. We find iron and copper on our series. We know that both of them are in that middle group that uses reduction with carbon. Since lead is right there in the same neighborhood, between them we can make a really solid prediction that it also uses reduction with carbon. And you know what? We'd be absolutely right. So when you boil it all down, it's not that complicated, is it? There are really just three groups. The unreactive metals, we just find pure. The middle ground metals, we win with carbon. And the superreactive metals, we have to force out with electricity. All of it dictated by one simple principle.
So next time you pick up an aluminum can, just take a second to think about the incredible journey that metal went on. It wasn't just found, it had to be liberated, forced out of its rock with an immense amount of electricity, all because of its high rank on that chemical scoreboard. And that, by the way, is exactly why recycling that can saves so much energy. It really makes you wonder, what other objects in your daily life have their own secret story shaped by this hidden chemistry?